All right, I'm going to show three problems that have to do with vector representation. And here's the first one. These are all on OneNote under Vector Reps. And number one says, find the representation of the vector 1, 2, 3 relative to the basis 1, 1, 0, 1, 0, 1, and 0, 1, 1. Okay, so what this means, you should translate this into language of linear combination. This is the basis, and I want to represent this vector as a linear combination of the vectors in this basis. So how do I write a linear combination of these vectors? Well, that's what I have down here. Right? General linear combination is right here. 1, 2, 3 is 1, 1, 0 times a constant plus 1, 0, 1 times a constant plus 1, 1, 1 times a constant. So here's your linear combination of the three basis vectors, and we set that equal to the vector that we want to represent. Okay, so that's what we mean when we say find the representation of a vector relative to a basis. All right? So how can we solve this? Well, it's very useful, and we've seen this before, to envision this right-hand side as the product of a matrix and a vector. Now, when we have a linear combination of columns, that's the same thing as taking the matrix formed by those columns times the constants in a linear combination. And you can verify that this linear combination of vectors is equal to this matrix product. Right? Well, we've seen that before. So we just need to set that equal to 1, 2, 3 and solve for x, y, z. All right? So I think that's the difficult step here, is to see when it says find a representation of a vector relative to the basis. All you have to do is set up this matrix problem involving the basis vectors, create a matrix whose columns are the basis vectors, and you solve the problem where you have that matrix times a vector is equal to the vector that you want to represent. So here I just went through the steps. These are very common steps. You take the REF of the augmented matrix, you get the result, pull out the result, and then you do the augmented matrix. You get the linear combination here. The -2, -1, 4 comes from here. All right, so that's how you solve that type of problem. Next problem. All right, given the linear transformation T of xy equals 3x minus 2y, 2x plus 4y, so this is a linear transformation. You can verify that it solves the linear transformation properties, or satisfies the linear transformation properties. So I want to find T of this following vector, where this vector is a linear combination of these two vectors. Now 1, 3, 2, 5 is a basis of C2. So here V, I'm representing the vector V in terms of this basis of C2. All right, so the problem is find T of V when V is expressed in terms of a basis. All right, well, we're going to use the same idea to solve this that we used for the first one. If we have a linear combination of vectors like this, we can write this as a matrix times the constants in the linear combination. Same thing I said for the first problem. Same idea. All right, so I've transformed this linear combination of vectors into a matrix times an unknown vector. All right, so that's what V is. Now we want to find T of V. All right, and we know that T of xy is this. That was what was given. Let's verify that I got that right. 3 minus 2, 2, 4. All right, so what did I do? I expressed this linear transformation as a matrix times a vector. I think that should be familiar also. Same idea. All right, so the linear transformation times this vector can be written as matrix times a vector. Now we want T of V. So we just need to plug V in for this xy. Don't be confused that I have the same xy here and here. These are just unknowns. They're placeholders. So I can replace this vector xy, this unknown vector xy, with the vector V. The vector V is up here, so I take T times the unknown vector V. What do I have here? I just have the product of matrices. Okay, so I take this matrix times this matrix, and I get this result, and then I can write this again as a linear combination of vectors. Right? All right, very good. So last problem along a similar vein is I want to find x prime, y prime such that x times minus 2, 7 plus y times 3, 4 equals x prime times 2, 2 plus y prime 1, 0. And you want to express, I'm sorry, I said this the wrong way. This should say express x prime y prime in terms of xy. So let's change that. Move that, switch that around, and we'll be good. So I want to express x prime y prime in terms of xy, and this is problem 3. All right? So here I have an equation where I have this linear combination of vectors, and I can express it also this way. Now notice that minus 2, 7, 3, 4, that's a basis of C2. 2, 2, 1, 0, that's also a basis of C2. So we're kind of changing from one basis to another basis. We have this linear combination, as I said, in terms of this basis, and I'm changing to a different linear combination. Right? So now I'm doing the very same old idea. Okay, so here I have this linear combination of column vectors. I can write this as a matrix times the vector of unknowns. Do the same thing on the right hand side. This linear combination of vectors is a matrix times a vector of unknowns. Now I want to solve for x prime y prime. What do? Well, I can multiply both sides on the left by this inverse matrix. If I multiply by this inverse matrix on the right hand side, it will kill this matrix and give me x prime y prime. And then on the right hand side it will give me my solution. All right, so let's just do that. Multiply by the inverse matrix on the left and on the right and do the calculation, and that gives me, on the left hand side it gives me product of matrices times xy. On the right hand side it just gives me x prime y prime, because as I said, this inverse times this matrix gives me the identity matrix. Okay, once I work out this matrix, I get the result. I express x prime y prime in terms of xy. Okay, so these three related problems, we'll have some chance to practice these.